Good morning. Let's begin lecture number 9. We'll start with a quick summary of lecture 8 recap, and if there are any questions, there were several interesting questions after class yesterday, and if there are any doubts, we can clarify them. So to quickly highlight the main contributions that we looked at in lecture 8 were the contributions of McDonald, the cellular concept, which consists of two important parts. One is frequency reuse, the other one is cell splitting. And between those two concepts, more or less we've been able to handle all the key elements that we needed to work with in the context of the design of a cellular system. So we would like to now move on to understanding some of the other elements. When we talk about frequency reuse, we talk about those channels which are exactly the same as our desired user is using. Those would be co-channel users. Then immediately on either side would be the adjacent channel, and then we have the next adjacent channel, and then the others. The adjacent channel ones are more or less handled completely by your receive filter. So the receive filter takes care of all of these. So we really don't worry too much in our frequency cellular system planning in terms of adjacent channel. Assume that you have designed a good receive filter and that you have. So co-channel interference becomes the one that we always have to worry about. Co-channel interference, and more or less the rest of the discussion in today's lecture is going to be focusing on co-channel interference. Now frequency reuse, as we discussed yesterday, will have the following components which I would like you to sort of keep in mind. We're talking about k channels per cell and n cells per cluster. So basically you are designing certain clusters of cells and you are able to give each of the cells k channels. So that basically says that the total spectrum that you have is n times k. Now that's what you are able to distribute, and as was clarified yesterday, you do not need to give k channels to each cell. You could distribute them unequally to make sure that you have unequal capacities, but at a baseline, designing it for uniform capacity would be a good starting point. A being the area of the cell, and M is the number of clusters that you need to cover the geographical region. Typically it would be a city, or maybe even larger than a city as well. So the total capacity, how many simultaneous calls that we can have, is n times k. That's the number of channels available in a cluster, times M, that would be the total simultaneous calls that are possible in the system. That's an important number for us to keep in mind. And you are supporting so many simultaneous calls given a spectrum which is proportional to nk. What is most important for us is that we would like to increase the capacity. Now increasing capacity will come at a price that you will pay, but we also have to make sure there is no possibility of outage. We said that in an interference limited system, the outage maps to the C over I, carrier to interference ratio. Again, I am neglecting noise, so I am not talking about interference plus noise, more or less neglecting noise and saying interference is a dominant part. That more or less says that the C over I that I experience for my desired user should never go below a threshold, C over I min. I should always make sure that is satisfied, and that's what is the condition given to us on the left. C over I, what I design with the appropriate margins should be always greater than C over I min. So this is the broad framework of the frequency reuse concept. We will now build upon it in today's lecture. Now cellular geometry is the basis for the discussion today. As we mentioned, we can look at any regular shape which will permit tessellation, and the three basic shapes that we looked at, triangle, square and hexagon. I hope you've done the calculations. Basically will tell you for a given distance, maximum distance between transmitter and the farthest point of the receiver, the area covered by a hexagon is the best. So therefore hexagon would be the one that will require a minimum number of cells to cover a particular area, and it also is a good approximation to a circle, which is what the coverage that you will get if you have omnidirectional antennas. So the other element that you will see very soon once you start working with hexagons is that it is very rich in symmetry. So one of the advantages that we have is a lot of very, very interesting symmetry, because a hexagon, a regular hexagon, consists of 6 equilateral triangles. So the minute you start looking at tessellations, you will see that the symmetries start to appear in very, very different forms. So for example, if I were to tessellate 3 hexagons touching each other at a common vertex and connect their central points, that forms an equilateral triangle, and that will repeat continuously. So if I have another observation, if r is the maximum distance or the side of a hexagon, it also happens to be the distance from the center to any of the vertices. The distance between the 2 centers, basically it will be the height of those equilateral triangles, twice of that. So basically you will get 2 times root 3 by 2 r, which will give me root 3 r. And again, that's a very useful point to remember, because whenever we tessellate, we are looking at distance between the centers, and usually in cellular geometry discussions, r is a parameter that you will have to choose. That will be based on the size of the cell. But for a lot of discussions, we assume that we can choose r to be anything. So if you choose r to be 1 by 3, then it basically says that you have unit spacing between the centers of your. So this is basically a normalized diagram, normalized values. You always have to make sure that when you are specifying the distance, are you specifying it in the normalized or in the real case? So what we will do is work with the normalized diagram, because it's very easy for us to work there, because centers between the hexagons will be unity. But when you translate it into actual design of the system, you must make sure you remember that there is a radius that will define the area of each cell. So this is a normalized representation. So we will, moving forward, we would like to keep the hexagonal geometry and keep leveraging the symmetries that are available to us in the cellular geometry. Okay? Now, first and foremost, you must get used to drawing a hexagon. So basically, hexagon is probably much easier to draw than the higher polygons, higher order polygons. Once you have a basic hexagon populated with hexagons touching on all of its 6 sides, that gives you a, so basically you have a single hexagon, and if you draw similar hexagons touching all of its 6 sides, you form a pattern that actually turns out to be the 7-cell cluster, and that is one of the very commonly used design tools for a cellular system. So basically the cluster would be along the blue lines. This would be the pattern that you would have, where you have a single cell, the red cell, with a hexagon touching each of its 6 sides. Okay, and you probably can draw it much faster than I can. So that blue shape now becomes a cluster. And now if you design your system using a 7-cell cluster, this shape would now get replicated. So notice that the cells must tessellate, the basic shape must tessellate. There's an additional constraint, because you're going to repeat the cluster size. You're not going to change the cluster shape as you move around, because then the geometry will get affected. So the clusters also must tessellate, right? You can't design some weird pattern, but basically these are hexagon lends itself to several patterns that the clusters themselves will tessellate. So again, keep that picture in mind, that the basic cell is a shape that tessellates, and the clusters also tessellate. Okay, one of the important tasks that we will do in this discussion is to calculate distances. Now, if I were to maybe go back to the previous slide, now if I were to think of this cell and I have a antenna or my radiating element at the center of this, and the farthest that a user can go from that cell would be at a distance of r, correct? That would be r. Now the key questions that will arise is, if my user is in the most disadvantageous position, that means with respect to my desired transmitter, I am at farthest point away from there. Now at this point, what is the interference that you will see? So basically you will want to know what is the distance of your mobile from your other base stations that are using the same frequency and therefore can cause interference. So basically you are interested in all other base stations and their distances from your mobile. Okay. So are you able to visualize? So you in a 7-cell cluster, you will find that there are 6 base stations, each one where you place the structure on all sides, and you will find that there are many base stations that will interfere, but there are 6 that are closest to you. You will have to find out those 6 and you will have to measure those distances. So there is a name given for those. They are called the tier 1 interferers. Tier 1 interferers, basically those interferers that are closest to you, and in this shape, if you draw it, you can visualize that there are 6 of them which are very close. Then there will be a tier 2, tier 3, tier 4, but most of the time we are concerned about the tier 1 interferers. We don't worry too much about the tier 2, tier 3, they are there. If you want very accurate calculations of the interference, you must take into account tier 1, tier 2 and 3, but a first order approximation, which is usually very good, is by looking at the tier 1. So the distances are very important for us to calculate. So let me just give you a feel for how to exploit the hexagonal geometry for quick calculations. Okay. So here is a 7-cell cluster, and we are basically saying that I want to know what is the distance between these 2 cells. Okay, there is a geometry, and I have and presumably they are using the same frequencies, and therefore I am interested in knowing the distance between. I am now asking for you the distance between the 2 base stations which are using the same frequency. Okay. Now the easiest way is to identify some pattern in the cellular geometry. So what would be the way is draw a line, the blue line, which is basically connecting along the centers of those sides, okay, until you reach that cell which is marked 2, and then from that point it's a 90-degree turn, and then you can basically form a right angle and find out what's the distance of let's call that as A, B and C. So basically AB squared plus BC squared square root will give me the distance that, so D is equal to AC square root of AB squared plus BC squared. That's the easiest way to do it, because there's a lot of interesting symmetry. So I want to calculate the distance AB. So it basically traverses along the altitudes of the equilateral triangles. If you notice, it is traversing. So basically if you think of an equilateral triangle here, equilateral triangle here, equilateral triangle, basically it's traversing along the altitudes. And root 3 by 2 is times r is the height of the altitude, and there are 5 such altitudes that it traverses. So 5 times root 3 by 2 whole squared, that becomes AB squared. So this is AB squared. Okay. AC squared is going along the line connecting the center to the vertex, that is R, and then it basically does half a side. Each side of the hexagon is R, so basically it will be R plus R by 2, so that is 3R by 2, that is BC. So this is BC squared. Okay. So again, it's once you see the patterns, it's not difficult. Just have to be careful. Are you going along the altitude of the equilateral triangle, or are you going along the side of the hexagon, in which case it will be multiples of r. If it's going along the altitude, it will be multiples of r root 3 by 2. So do an example calculation and find out what the distance is, because that's a useful parameter that we'll be coming back to discuss several times in the course of the understanding of the cellular systems. Okay. So is this the method of calculating distances? Identifying a right angle triangle identifying it in terms of their two sides, in terms of combinations of height of the equilateral triangle and the side of the hexagon. So basically known quantities used to estimate the distances. Okay. Hopefully once you do it a couple of times, I'm sure you'll find it that it's fairly straightforward. You'll almost be able to see, but it's probably a good idea to draw a line and do it so that you don't make a mistake, that you are getting the angles correctly. Okay. Now taking this geometry discussion to the next level is to enable us to understand the design of a cellular system. So we are now going to introduce a coordinate system to number or label the cells, and notice that if I want to draw a line connecting the centers, so one axis, the y-axis is nicely aligned in this case, but if I look at the x-axis, it is doesn't go through all the centers, it goes through some centers, it goes through some edges. Now I don't want that, I would like to be able to work through the centers of the hexagons, so which means that I cannot use the x-axis, I would have to sort of rotate my axis, and that would be the u axis. It's basically the two axes that we have, u and v, are at an angle of 60 degrees, not orthogonal, not 90 degrees as you would have in a xy coordinate system. So we are going to introduce a coordinate system which has an angle of 60 degrees. Okay, that's and again this is not a problem, it's just that I am going to label them in the following fashion. So I label them starting with 0, 0, I label the centers as 1, 2, 3 and 1, 2, 3 on this direction. So for example, this blue dot that we are seeing has got 3 units along the u axis. So first coordinate is u 3, 2. It should be 3, 1, sorry, it is not 3, 2, it should be 3, 1. Okay, so basically this is how we would label the UV system. So I will denote any point in terms of a u coordinate and a v coordinate. So basically u1 v1, u2 v2, and in any coordinate system the most important element is the distance between 2 points which are denoted. So I'm interested in the distance between points 1 and 2 which are given by the coordinates u1 v1 and u2 v2. So I'm sure that when you did coordinate geometry, when you move away from a 90-degree coordinate system, the distance measure changes slightly. It's no longer the Pythagorean relationship. So let me just write it down again. It's something that you're probably very familiar with. So basically it will be u2 minus u1 whole squared plus v2 minus v1 whole squared plus u2 minus u1 into v2 minus v1 cosine of the angle between the two. So and if it's 90 degrees, so that third term will go away, but if it is in this case it will come out to be u2 minus u1 into v2 minus v1. Again, if you do a simple geometric basically looking at the distance description, you can confirm that this is what it will come out to be. So in this UV coordinate system, if I give you 2 points, if it were an orthogonal one, you would just take the first 2 terms, but it's at a 60-degree angle. So basically we would introduce a second term that is introduced that tells me the distance measure. Okay. And for ease of calculation, you can always refer your distance computation to the origin. That means if I map P1 to 0, 0, that means P2 then gets mapped to the points as shown here. Okay. So an easy way for us would be is to we'll denote the one of the points as 0, 0 and the other one as I, j, where I is equal to u2 minus u1, j is equal to v2 minus v1. Okay. So I want to know dij. So that will be square root of I squared plus j squared plus ij. So that's my UV coordinate system, It is a slightly different from what we are used to in traditional geometry, but again, given the hexagonal tessellation that we are doing, it's a more convenient reference system for us to work with, and it gives us a certain flexibility to label these systems. Okay? Now, I now want to relate. This is probably the most important reason why all this has been, all these have been introduced. Now, I want to go back and ask you to think about the following elements. I want you to think about how this tessellation is happening. So basically, I have a cluster. Then I place these clusters in a tessellation form. Now, I want to know how many tier 1 clusters are going to be there. Okay? So, to answer that question, we have a interesting way to do that. Let me give you the method first, and then the rationale follows. Okay? So, let us say that I have a basic cluster, which is the 7-cell cluster. So, let me just highlight it for you. So, this is my central cell around which the cluster has been built. So, the cluster, 7-cell cluster, which I am sure you are now able to draw fairly quickly. You can highlight it. Sorry, it should be, that should be the cluster. Okay, that's the central one, and then the cluster around it. Okay, now how to identify the location of the clusters that will come around the basic cluster? So, which means that first find the center of the cluster, position that, and then basically place the cluster around it. So, here is a algorithm, very simple one, from the hexagonal symmetry understanding, which says that if you want to identify co-channel cells, what you need to do is basically move along the coordinate system some integer number of locations. Now, for example, let us take the translation u equal to 2, v equal to 1. So, basically from the center point along any of the sides of the hexagon. So, basically I have chosen to move along this particular direction, move to two centers. So, the cell number 4 will be the first center, and the one after that will be the second. So, u is equal to 2 along that. Then I turn counterclockwise 60 degrees, because that moves me from the u axis to the y axis, to the v axis, and then move number of coordinates along that. So, u equal to 2, v equal to 1, moving in this particular coordinate system tells me that I can go move 2 in this side and then 1. So, that tells me that I have not yet told you that this is for a cluster size 7, but I am just giving it to you as a information. So, for a cluster size 7, u equal to 2, v equal to 1 gives us the location of the other centers. Now, obviously you should be able to do u equal to 1 and v equal to 2 also. So, if you were to do u equal to 1, v equal to 2, let us try that in another direction. So, from here u equal to 1 will be one cell you move, then rotate counterclockwise 60 degrees, move 2 units, 2 cells. That will tell you this is the location of the, if you use that shift, it will come there. Notice that, and now you have to repeat it for all the sides. So, we did the red one from this side, then if you do the red one from the next side, let us do that. Red one from here, move 2 units counterclockwise 60 degrees, that gives me this center. Then likewise, if I did from the other side 2 units counterclockwise 60 degrees. So, you can see that basically like a wheel, you get all the locations. Now, if this is a valid way of obtaining the locations of the next cell that is using the same frequency, co-channel cell, basically it is a method for identifying your co-channel cells. Okay? We will show that this is correct, this is a valid one. So, if this is the way by which we do that, then I have a very, very important observation to make. How many tier 1 co-channel cells will there be? 6, because the only way I can locate it is by going along the side. I have only 6 sides. So, this is a very, very important observation that tier 1 will always consist of 6 interferers. And of course, using this method, how do I get to tier 2? From this cell, use the same principle, or let's take from this cell, I can move 2 units, turn 90 degrees, 60 degree, counterclockwise 60 degrees. That will be another cell that's using the same frequency. So you can basically, in a hexagonal cluster, you can pretty much locate all the cells that are using the center frequency. And once you have those center frequencies, just placing the clusters on top of that is relatively straightforward. So the important concept is the link between the clusters, the size of the clusters, and the locations of these co-channel points. Okay? And we need to be able to pull all of them together, and it turns out it comes in just one step, and that's the beauty of the hexagonal geometry that we are going to take up. But before that, let me just sort of, just for interest sake, what are some basic clusters? Cluster 4 is a cluster that will tessellate. So basically you can draw 4 of these, and then you can see that you can actually tessellate with this particular shape. N equal to 4, there's another numbering that will also allow you to tessellate. So basically any combination of 4 will tessellate. Okay. N equal to 3, you can draw, and 3 and 4 are probably the most interesting ones that we can do by hand. 7 is easy, but anything beyond 7 becomes a little bit cumbersome. Keep in mind that whatever shape of the cluster shape must tessellate. I think that we already mentioned, but good for you to keep in mind. Okay. Now we move on to a very important question. What is the valid cluster? What are the valid cluster sizes? That's question number 1. And we have to basically verify the algorithm that we have shown, that the way to cluster it. One is of course to try it out. That's a way to do it. Verify the method of locating the co-channel cells. So that's the second aspect, co-channel cells. Okay, that within the hexagon. So these are the 2 things that we would like to answer, and we will come back to answering that in a little bit better fashion. Okay, so here is a very dense picture. Let me take the the center cell, the one that is shaded blue, and I am going to do using the algorithm that I did. I'm going to move 7 units in one direction and 0 in the other. That's a valid combination. So basically along the centers, notice I've gone along the centers. Let me draw it with a different color. I go along the centers. This is cell number 1, 2, 3, 4, 5, 6, 7. And like that I have gone on all 4 sides. Okay, that gives me a location of my co-channel cells. Now keep in mind that this is very closely tied to the fact that the number of co-channel cells is going to be 6, and that can easily be verified, because I can when I go from each of the sides of the hexagon, I get I've shaded all the blue hexagons that are co-channel cells. Okay. Now here is a scenario that I don't know the cluster size, but I want to determine the cluster size. I've determined the co-channel cells. Now think of it that these clusters, whatever the shape of the cluster has to fit around each of these co-channel cells. And if you think of a large cluster size, then what you will find is that the shape that actually fits should approximate a hexagon, because only then 6 of them will fit around with these 6 points as the centers of those hexagons. So that's a sort of a maybe it's for some people it's very easy to visualize. That only then it will fit. But you may say, well, some of them are going on, but approximately a hexagonal shape is what it will need to actually tessellate on this framework. So this actually shows us a way to validate the assumptions that we have made, and let's quickly see if we can work on that. So here is the piece that we would like to work with. Basically we have a small hexagon, and then we have a large hexagon. So a small hexagon, let us say, has got radius r. The area of the small hexagon is 3 √3 by 2 r squared, right? That's the area of a small hexagon. The area of a small hexagon. Now, if R dash is the area of the larger sort of invisible hexagon, that's the one that I'm trying to estimate the cluster size. So, given that it has to be a pattern of 6 and it's got roughly a hexagonal shape, I'm assuming that this is the area. So, if the radius of the large or the size of the larger hexagon is R dash, the area that I'm going to work with is 3 times root 3 by 2 R dash squared, which is same as 3 times root 3 by 2 d by d squared by 3. 3 and 3 will cancel, that gives me root 3 by 2 d squared. So, that is the area of the larger hexagon. So, the key step says the cluster size n is given by area of the larger hexagon divided by the area of the small hexagon. Approximately, some of them are partly covered on one side, partly covered, but actually if you look at it, a whole number has to emerge, and that should be the area of the larger hexagon by the smaller hexagon. Okay. So, the area of the larger hexagon divided by, that is be root 3 by 2 d squared, that is the area of the larger hexagon. This is 3 times root 3 by 2 r squared. That's that should be approximately the cluster size. Now, let me take 2 paths to it. One is going to take the path of the normalized pattern. In the normalized pattern, we said that we would assume R to be 1 by root 3, so that we can get the right shapes. So, if I substitute R by root 3, then I get the cluster size. In a normalized hexagonal grid, the normalized one will be equal to d squared. D squared. Okay? That is the distance between the 2 co-channel cells, between the the centers of the 2 co-channels of the large hexagon. Okay. Now, very, very important. What is d in the normalized framework? D squared. We showed that using the UV coordinate system, this will come out to be I squared plus j squared plus ij. So, the cluster size in a normalized framework should be I squared plus j squared plus ij, because that's what tells me that if I were to carefully draw the cluster, this is what the size would be. Making sure that I get all. So, the important element is that we have these small hexagons, which are the co-channel cells. To visualize the cluster, I am saying that it has to be a pattern that surrounds it, approximately a hexagon. There will be some jagged edges, but effectively it should approximate an hexagon, and that's the estimation that we get. Now, if it is not the normalized side, let's write down the relationship on this side. Basically, what you will get is d by r is equal to root 3n. And if you take r to be 1 by root 3, you can get back the original relationship. So, basically, the cluster size, which for us it will be thinking of it in terms of the geometry that we have developed, and the coordinate system is given by I squared plus j squared plus ij. And another important relationship that emerges is d by r is equal to root 3n. Okay. So, now let us go back and look at the valid cluster sizes. So, cluster sizes basically says I can take I, j, then I have I squared plus j squared plus ij. So, if I were to take the combination 2, 1, I get a cluster size 7. Remember that that was what we had verified, and of course, if I do 1, 2 also I will get 7. I can do as long as I and j are integers, right, because in the coordinate system that's what we have, those are the points at which the centers of the hexagons lie. So 2, 0 will give me a cluster size of 4, 0, 2 will also give me a cluster size of 4, 1 and 1 gives me a cluster size of 3, 1 and 0 says it's a single cell cluster. That's not really not a cluster, but you can now go on and verify various combinations. You can show that n equal to 12 will come, n equal to 21 will come. As you go further, the cluster sizes, they're not too many, you will basically get larger sizes. Okay. So that's an interesting observation. I would like you to be comfortable in terms of the arguments that we have presented and the ability to work with this observations. Okay, now I want to move to a very important element from the previous discussion. So the previous discussion, we identified that there is a ratio called D by R. This is called the co-channel reuse ratio. Co-channel reuse ratio. R is the radius of, or the maximum size of one cell. D is the distance between the co-channel cells. So this is the co-channel reuse ratio. Okay, so it is a parameter that once you have designed your cluster size, you can then say that D by R has got this relationship, and D by R is equal to root 3 n. That's a relationship that we have obtained. So let's spend a few minutes, because this is a very important parameter. It actually is denoted by the letter Q, in some sense to denote that it's a quality measure, and we will justify the fact that it is a quality measure. Now what happens if Q is small? If Q is a small value, this basically implies D by R is a small value, right? D by R is small. This implies that n is small. Am I right? N is small. Your cluster size is small. So the price that you will pay is that C over I will be low. But the good thing about this is that capacity will be high. Capacity will be high. So the trade-off between capacity and quality comes up, and we have to. So the constant thing would be is what is the smallest Q with which I can work so that I can achieve the target C over I. That's going to be a very, very important element. Now it may seem kind of obvious, but let me just say it anyway. Q becoming larger, because the D by R ratio is directly related to n, larger cluster size, visualize that, basically says that my co-channel cells are going to be further away geographically. I have not changed the capacity, but because the co-channel cells are further away, the C over I is going to be better. So again, there is a important understanding of the impact of this D by R ratio, and we will build on this a little bit more. Any questions on what we did as the argument for the cluster sizes, or the UV coordinate system, or the consequent observation about the importance of D by R?
Sir, increasing R will automatically decrease capacity because time.
Decreasing R.
Increasing.
Increasing R. Okay. See, increasing R, what it does is increases the size of one cell. If you don't change the cluster size, basically what will happen is your co-channel reuse ratio does not get affected, right? So increasing R without changing N will not help us in terms of capacity. Basically the cells will become larger.
I'm saying it would hamper us because in the same geographical area your number of clusters will fall.
Exactly, that's correct. So increasing the area of a cell means that your cluster area is going to increase. You will have fewer clusters to cover the geographical area, and therefore the total capacity of the geographical area will go down. Correct. That's a correct observation. Okay. So let's move into a couple of very, very important elements, and basically Q is equal to D by R co-channel reuse ratio. Our interest is to calculate the carrier to interference C over I ratio, co-channel interference ratio. So now I want you to visualize this signal power. I have only one source of desired signal, that is PS. Now the interference can come from multiple interferers. So let me call the index as I equal to 1 through some I naught, some number of interferers. Why is my interference number not fixed? Depends on whether I am including tier 1 only or tier 2, tier 3 also. The numbers would increase, the cluster size will determine the number of interferers, it will also determine whether I am sectorizing the antenna, lot of things will affect me. So it is some number, some integer number which is I naught times I all the interference powers. Okay. So I naught is equal to the number of co-channel interferers, and I have to determine which of these are significant and apply the appropriate number and include their powers. And I is the power of the ith interferer, power of the ith interferer, interfering signal, interfering base station, interferer signal, okay, and PS is the signal power, signal power. Okay. Now a very intuitive question. Now let us go back and visualize the scenario that we are working with. Okay. Now let us say that I am looking at the interference scenario. I have a issue of interference. Interference can happen on the downlink and it can happen on the uplink. Which is the more difficult scenario for me to work with? So downlink means that I am talking about transmission from the base station to the mobile, correct? So it is in the arrow, in the direction of the arrow that I am transmitting, and I get interference from these neighboring base stations. Uplink means the mobile is still at the edge of the cell, it is transmitting upwards. Now it could be the uplink transmission can come from other mobiles, right? Uplink and interference. So who's very close to the edge of its cell and therefore is causing interference to my base station. So basically I can think of these two positions in cell A, which could be the ones where the mobiles sitting there could cause interference to me on the uplink. Okay. So you can visualize the scenario. The downlink, the interference comes from all the other base stations. Uplink comes from mobiles which are at the edge of their cell communicating to the base station. Now which of these is the more troublesome, which is likely to have a poorer C over I? Okay, why do you say downlink? Very important, because the base stations typically transmit with higher power and therefore are likely to cause a much worse C over I. Now uplink, first of all, it's a mobile transmitting, and the other important factor to keep in mind is that the base station has got multiple antennas which are intended for interference suppression. So it has ability to deal with interference in a much better fashion than the mobile itself. So the downlink is the more difficult situation. Downlink is C over I is what we consider, okay, because that's the more problematic link. Downlink is worse than uplink from a C over I perspective. So always we look at the downlink scenario. Okay, so let's build on that assumption. Okay, so basically we are looking at the downlink. We are looking at the distance of all the interfering cells. So here is what this equation can be written in the following fashion. Now the desired signal, it is at a distance r from the base station. So basically this is r raised to the power minus n, where n is a path loss exponent, proportional to path loss exponent. And the proportionality constant will be removed because I am going to take the denominator also has got the same proportionality constant. Now the number of interfering signals is the same, I equal to 1 to I naught. This will be di raised to the power minus n, the distance of the base station to the mobile. So we are basically looking at the downlink scenario. Okay, so base station I to the, which is interfering base station, to the mobile that is at the end distance. Now, if you look at the diagram, this is what it is going to be like. If you notice that I have the desired base station which is sitting here, this is the desired signal, and the black arrows are all the undesired interferers that are coming in. Okay? So, if I were to write it down very precisely, basically if you look at the cellular geometry, you can then you can write down the expressions very. Now, D is the distance between the co-channel cells, that is D. You can actually relate the distance between the base station to the mobile to something very close to D. Now, in this figure, what it says is this particular mobile is at a distance D from this base station, from the base station, from this base station. It is at a distance D. From this base station, it is at a distance D minus R, because D is all the way up to here, right? And this is D, and we know that is R, so this is approximately D minus R. So, this is approximately D. This is also approximately D minus R. This distance is approximately D plus R by 2, approximately, this is approximately D plus R. So, basically in terms of the known terms. So, if I were to ask you to write down the C over I expression for this, this would be, I have taken only the tier 1 interferers. This is only tier 1 interferers. So, this would be R raised to the power minus 4, and I have taken path loss exponent of 4 divided by, there are two base stations which are at approximately D minus R distance, which will be D minus R raised to the power minus 4. There is one base station at D minus R by 2 raised to the power minus 4 plus D raised to the power minus 4 plus D plus R by 2 raised to the power minus 4, and one more term D, 2 times D plus R raised to the power minus 4. Do I get 6 interferers? 2, 3, 4, 5, 6. Okay, 6 interferers. Okay. Now, if I make the assumption that D is much larger than R, which is typically the case if I have large cluster sizes, then I can approximate this distance, this C over I calculation, as R power minus 4 divided by 6 D power minus 4. So, this is the case where the number of interferers is equal to 6, and therefore, I get 1 by 6 D by R raised to the power 4, or D by R raised to the power n. Okay. Notice D by R is the co-channel reuse ratio. So, this is nothing but 1 by 6 Q raised to the power 4, and this is a quick approximation. Okay, and this is a way by which we can make a quick estimate of the interference scenarios that we are going to encounter. So, let us look at one quick example, and then we'll close with that, but we'll pick it up from there. Take a cluster size, let me use a different color, n equal to 7, cluster size n equal to 7, only tier 1 user interferer, so I naught equal to 6, path loss exponent equal to 4, and omnidirectional radiators, omnidirectional. So, all the base stations on all sides can create interference, basically all 6 sides will create interference. So, if you apply the approximation, C over I is approximately 1 over 6, D by R is root 2 times root 3 n raised to the power 4. Okay, so this can be estimated. This comes out to be 73.5, which is approximately 18.7 dB. So the statement that we can make is, if I use a 7-cell cluster with omnidirectional antennas, the interference from the first tier 1 interferers is going to be approximately resulting in a C over I of 18.7 dB. Okay? Now, very important for us to understand what are all the factors that are impacting the capacity or the C over I. C over I is being affected by the Q factor, D by R ratio. It is also being affected by N. If it's being affected by Q, that is related to the cluster size N, because Q is equal to root 3 N. So basically C over I depends on N and N. Very interesting. Cluster size and path loss exponent. And in noise limited systems, a higher N was your enemy, correct? Higher N was enemy, because what happened? Because the signal faded away much faster, and therefore your cell sizes shrank, and therefore your cost of your system increased. What happens in a C over I situation? If your path loss exponent increases, what happens? C over I is D by R. D is greater than R. It's a number greater than 1. So in the case of C over I, a higher exponent is your friend. Why? Because your signal degrades faster, the interferer signal degrades even faster, so C over I is actually better. It's a very, very interesting, so in a noise limited system, you don't want high path loss exponent. But in a C over I system, you say, oh good, I know I'm very happy if the exponent increases, because I'm going to have better C over I. Okay? We'll pick it up from here in the next class. Thank you.